Rachel Blackstone, and this is my Lab 2 report for Physics 2211, which encounters dropping an object lighter than a rock. This will show non-constant velocity, which will mean that the net forces acting upon this object will not equal 0. I began by videotaping a dollar bill being dropped from about the height of 2 meters and imported this into Tracker. You can see I put a ruler against the wall as a calibration stick and then marked the distance it fell after each time frame. We can see that the points got a little further away, showing that some force was accelerating the object. We can then look at our graph data from our observed data here. The only hiccup we have being around the 0.45 second mark. This may be because it hit the wall or just imperfect videotaping skills, as it was hard to always be able to see such a small object on camera. Next, we move to our Python code, or our modeled data. First, let's set up some initial conditions. We can see that the ball's mass is 1 gram, or 0.001 kilograms. Also, our initial conditions being the ball's position at 0 and the ball's velocity at 0, since we are dropping it from rest. Time is also at 0, since this is when we choose to start. Our delta t time step is very small, even smaller than the last video. This is to have the best modeled predictions. We also need to set g, our gravity acceleration, as 9.8 for 9.8 meters per second. Also needing to set a y-axis vector, unit vector, as 0, 1, 0. We will worry about b later. Next, let's enter the loop. We'll make the final time equal to 0.7, since this is when the last motion of the ball was observed. We can see that our weight vector, or the vector of the weight force, or the force of gravity on the ball, is equal to negative ball mass times the gravity times the j hat. For now, our F net is W. We can predict our ball's new velocity and ball's new position exactly how we did in Lab 1. When we run the code, we can see a nice curvature of the line and a very easy drop of the ball as accelerating a little more as it drops over time. Looking at our model versus our experimental, they look similar, however, our model tends to drop much faster than that of our experimental value. For this, we added a drag force constant, proportional constant b for the magnitude of this drag force. We found that when we add a drag force of 0.00155, we get a final position of negative 1.728, very similar to our observed final position of negative 1.722. Also, we will add arrows to our new model. The arrows' positions start from the ball's position. This is because they're coming from the center of mass of the ball. The length of the arrows are equal to W for the weight force and Fd equal to the drag force, multiplied by some arrow scale. This arrow scale is there because the weight force and the drag force have different units, meaning we need to add some sort of constant for us to be absorb their proportionalities to one another. Now let's see what happens when we actually run the code. Slow because my computer's freezing up, but also see the yellow arrow pointing out. Some conclusions we may have. Dropping an object allows the Earth to act upon the system, gravity accelerating downward. We can see that the magnitude of the weight force is equal to mass times gravity. To get the actual force, all we need to do is multiply it by the unit vector, 0, 1, 0. Also, drag forces slow down the object, not allowing it to accelerate perfectly. We can calculate the drag force by some constant b times our ball's velocity. We find our F net by multiplying the magnitude of the weight force times its unit vector plus the drag force. This is what shows our model. This is how we get our model here. Thank you for watching this video.